Okay, in this slide we start talking about soil. We introduce soil into the picture, even though we actually in the previous slide the gradient, the hydraulic gradient is used very much in geotechnical engineering and soil mechanics. That's just a definition though. Here we're going to start actually thinking of flow through soil. Now, in the case of civil engineering and geotechnical engineering within civil engineering, it is often the case that the flow that we're concerned with is the flow of water, and water flows very slowly through soil. Okay? When we have drains, filters, etc., even in nature, because the water has to grind against a lot of surface when it goes through a soil, a lot of surface of the particles, the velocity is very low. So what happens is we neglect the velocity head for total head calculation in soil. So instead of having total head equal elevation head plus pressure head plus velocity head, which is the truth, okay? This is what is the true physics. We say, look, the velocity head is so low compared to these other two that we're going to say it's zero. So we just basically neglect it. And we are left with a simplification of the equation. Okay? So from now on, the total head is going to be the elevation head plus the pressure head. Now, if you one day have to go into, let's say, out of civil engineering into civil engineering related fields like petroleum engineering, okay, or reservoir engineering, etc., you may actually realize that you have to bring back that H sub V, because in those cases there are locations in a reservoir, for example, where the fluid flows very fast. That is, for example, next to a well, okay? But for general or civil engineering purposes, this definition is perfectly fine. It's the one that we use. Okay. Now, here is a very important slide. Not only because of the definition that we have down here, but because you're going to see the so-called profile of a site, basically from now until the end of the course, okay, and into foundations engineering, etc. And even when you go and work in the field, if you're going to work as a geotechnical engineer, you're going to see this drawing. What is it? It is a cross-section of the site. Here's a tree, okay, that's the ground surface. Here's the water table location. That means that if you're up here standing, okay, and you start digging a hole, you'll encounter dry or moist soil, and all of a sudden you're going to encounter saturated soil. Remember S? Degree of saturation is 1 or 100% below the water table. This water table, which is the location of the groundwater, is different for every place in the world. Okay, in some places it's right at the ground surface. In some places it's very deep. Some places it's above the ground surface. In that case, you have like a lake. Okay, and so what we generally do is we say, look, here's the site. We stand on top. Here's the tree to denote that that's the ground surface. Okay, and here is a layer interface. So this is soil, and this is rock. If you continue to dig anywhere in the world, eventually you will reach what's called the bedrock, which is just a rock mass, okay? And of course there's layers of rock and all that. You keep going, you go into the mantle and all that, but we haven't actually reached the mantle yet. Physically, that's very far. So we generally, of course, constrain our engineering to the crust of the earth, which is actually quite thick. So we're basically at the very, very thin, sub-layer, let's say, that surrounds the earth. That's where we work. Okay? Now, here you may have 2 or 3 layers. Clay, silt, sand, rock. Or maybe clay, clay 2, sand, rock, etc. Right? So you're going to see this is called the profile. Okay? Profile. You're going to see this type of drawing a lot, okay? And that's what we use to map our systems. You know, the pile goes all the way to this layer, or does the pile go all the way to that layer? Pile is a foundation system. What about the shallow foundation? Is the shallow foundation going to be submerged in the soil like this, or is it going to be at the ground surface for our structure, etc., right? Okay. Very important slide, because we introduce here the profile. All right. Now, going back to flow and pressure and... Apologize for that. Okay, sorry. So, back to flow and flow concepts. Here we have a point. This point is located at a certain distance from the bedrock, okay, and at a certain distance from the ground surface, and at a certain distance from the water table. Okay? Now, if we insert a tube, okay, so that the end of it touches that point, and that tube is that piezometer we talked about, then the water table, the water will rise inside the tube to denote, remember that this is a sensor, to tell us what the pressure head is. Okay? So the pressure head at a point within a solid layer is the distance from that point to the water table. Okay? Now, what happens if the water table is down here? Well, the point is above the water table. So we assume that this point is in a location of dry soil. There's no water. So the pressure head is zero. There's no water. We cannot even calculate the pressure head. Okay? You could say, well, hold on one second, the pressure head is negative. No, the pressure head is not negative. The pressure head is nothing. We don't even think about it, because the soil, the point, is in soil that is dry. That is in the case where the water table is here. But the water table is actually up here above the point. So the pressure that the water feels in the voids is associated with this distance, the pressure head. Okay? It is the same thing as a tank of water, just that the point is now submerged in saturated soil, not just in a tank of water. But it's the same calculations apply. Okay? Now, here it says pressure head at A, that is that red arrow, right, that distance. Okay? And so now we can actually define what is the pressure. And this is the hydrostatic pressure. Why hydrostatic? Because the water is not moving, first of all, and the water is not suffering a pressure that is not due to its own self-weight. The reason why this point is under water pressure is because there is weight of water above it. Okay? And the only reason there is a pressure at this point is because of that. Now, there could be, for example, an explosion here, and that would probably pressurize the water with a wave or something for just, temporarily, and that would increase the pressure head, and the water would probably rise up and come out of the piezometer or something, right? But that's not what we're talking about yet. We're talking only about the static case where the pressure at a point is only due to the weight of water above that point, and the water is not moving. Okay? So that pressure head is the hydrostatic pressure head, and therefore the pore water pressure, the water pressure at that point, is the hydrostatic pore water pressure. Okay? How do we calculate it? Just like we do for fluids. For fluids we generally use P for pressure. But we don't do that for soil mechanics because P usually stands for a load applied. Okay? In solid mechanics, and remember that in geotechnical engineering we have fluids and solid concepts combined. Okay, so we use the letter U for pressure of water. Okay, H, the little h stands for hydrostatic, so hydrostatic pore pressure, and as you know, the equation for this, or the definition, is the pressure head times gamma water. What's gamma water? You have to know this by heart, 9.81 kilonewtons per meter cube, or 62.4 pounds per cubic foot. This has to be known by heart. All engineers have to know this. Okay, sorry, let me show you right there. Okay, so 9.81, 62.4, you have to know this by heart forever. Okay, let's go back down. Now you may ask, well, hold on one second, why is it called pore water pressure and not just water pressure or pressure? Well, we would like to have these three words in the definition or the name of this U, because we know that the water is in the pores, okay? And so we make a distinction in soil mechanics where we say that the water pressure, the U, is actually the pressure of the water in the pores. Okay, we just want to make sure that we remind ourselves always that the water is in the pores or in the voids, and the UH, hydrostatic one, or just the U, if you want to just say pore water pressure, that would be just U, right? That pressure is the pressure of the water that is present inside the pores. That is what the water in the pores feels this pressure. Okay? Again, if the water is in the hydrostatic condition, then it's the hydrostatic pore pressure. By the way, this definition is also something that you have to memorize, not for the course only, but for your whole engineering career. This must be known. Okay? This is something that all engineers know, so you have to know it too. Okay, next slide. We are going to introduce in this slide another pore water pressure. Okay, it's this one right here. But the idea here is that you kind of have this in your mind before we actually get to it later, because it's going to play an important role in strength and in the formation of soil with time. Okay, but we're going to introduce it here for the sake of you know, having it again in the back of your mind, knowing that there are actually two types of pore pressure. The hydrostatic pore pressure, which is the one that we just talked about, is due to the hydrostatic condition only, meaning that the water doesn't move, and the only contributor to pressure is the weight of water above a point. Okay? The distance, the pressure head. But essentially the weight of water present above the point. This other pore pressure is called the excess pore pressure, which means in addition to. Okay, so excess means in addition to. So U excess is the excess pore pressure, meaning the pore pressure in addition to hydrostatic. Okay, hydrostatic is always there, but we may have an additional pressure that is in addition to hydrostatic. That's called the excess pore pressure, and that is due to additional processes. Remember in the previous slide we said that if there's maybe like an explosion here, okay, and sends a wave or maybe even a shock wave through the material, then the pore pressure may rise. The additional rise of pressure is the excess pressure, okay, the excess pore pressure. Or maybe if we start constructing here too fast, this soil may actually exhibit what's called consolidation, essentially, after the pore pressure rises beyond hydrostatic. Okay, so those are additional processes that we sometimes impose in the field when we construct. It doesn't have to be as dramatic as an explosion. We can essentially construct faster than the water can drain out of the soil, and in that case we'll get UE. Okay, but I'll let you learn more about that later on when we actually get back to it and we get into how to calculate it and all that. For now, just realize that there are two, and if we add them, we get the total. Again, like in this course, no subscript means total. Okay? Like total volume, total head, total mass, total pore pressure, etc. No subscript means total. Alright. Next slide. You have actually seen this before in fluid mechanics, but here we have drawn a profile on top of what you have seen before. Okay, so first thing to make sure that is that we say here is that this is the type of engineering drawing that we use in soil mechanics and in geotechnical engineering. Okay? What is it? We have a plot. This is U, H. Look, an arrow. That means a plot, an axis. UH versus depth. Okay? And here is the curve. Right here. It's actually a line. Okay? So we have a plot. But we have placed the plot on top of the profile. Here's the tree. Okay? Here's the depth. Bedrock is down here, let's say. So we usually, in soil mechanics, in geotech engineering, we usually draw the profile, and on top of that we may draw different plots denoting the stresses and how they change with depth. Okay? Or the pressure, like in this case the pore pressure, and how it changes with depth, which is what we're going to talk about right now. But it's important that you get accustomed to looking at plots and drawings together in the same figure, because you're going to be drawing that if you take, for example, foundations, or if you continue to take this course, which of course you are going to continue. So this is just a reminder of what the hydrostatic pore pressure is. It's gamma water times the pressure. Okay, that is something that you have to know always, not only for this class but for your whole career. Okay, now let's look at what's happening here. Here what we have is essentially something that is very simple. It is a plot of pore pressure versus depth. So what is, if we look at the profile, let's just look at the whole drawing, but look at just the profile part of it. Here's the ground surface, here's the water table, here's the tree, right? What is the pore pressure here? 0, because there's no water there, right? What about here? 0. At any point above that water table, any point, the pore pressure is 0. What is the pore pressure right at the surface of the water table? 0, right? And that's the first point in our plot. What is the pore pressure at this point? Well, that point is a distance Z1, ZW1, okay? That's kind of a weird subscript, sorry. So it's the depth below the water table, number 1. Okay, but what matters is the distance. That is the distance, right, from this point to the water table. And that is the pressure head. The pressure head times gamma water, which is 9.81, is equal to the pore pressure. And that is this value. Sorry. Okay, so you can see the plot. This is a plot. X-axis, Y-axis, or whatever you want to call it. Okay? That's this value. What about at this point over here? Well, that's the pressure head times gamma water. It's that pore pressure. That's the value. And we keep going. And as you can see, the pore pressure, the hydrostatic pore pressure, is linear with depth. It increases with depth, just like it increases if you go scuba diving. The deeper you go in the pool, for example, the higher the pressure you feel. Same exact thing. Just that in this case, there is soil. Okay? So the water table is inside the soil mass. The soil below the water table is saturated, and the soil above it is either moist or dry. We're going to assume that it's dry. Okay? So this could be a little bit kind of confusing plot or figure, but I think if you spend some time looking at it and realizing what it is, it's just a drawing and a plot, one on top of the other, then you realize that it's just a plot of pressure versus depth. Of course, it starts from the water table, because above the water table there's no water. Okay? Okay. That is, of course, if we assume that the soil is dry above the water table, which we do. For this course, at least, we're going to do that. Okay, so this is the first part of these lecture slides. Then we're going to, after this, we're going to have another video where we talk about the next couple of slides. Okay?